In this video, we'll go over section 10.2, correlation of chapter 10 in the textbook. There are two parts for this section. The first part is it's about the introduction to the linear correlation coefficient R, which is a number that's used to measure how well that the pair sample data fit into a straight line pattern when you graph them. Using the sample data pair, we can find the value of the correlation coefficient R either by using technology or we can use formula, and we can make some conclusion if there is or there is not a linear correlation between the two variables. So in this section we consider only linear relationship, which means when graph the points approximate a straight line pattern. And then in part 2 we will discuss the methods of hypothesis testing for the correlation. So part 1, the basic concept for correlation. The definition: a correlation exists between two variables or two things when the values of one are somehow related or associated with the values of the other in some ways. A linear correlation exists between two variables when there is a correlation and the plotted points of pair data results in a pattern that can be approximated by a straight line. And we can often see a relationship between the two variables by constructing a scatter plot or just plotting the point on the graph, and we can see that they should form into a straight line. Now, if I have two scatter plot here, as you can see, I can plot all the data point here and there. Now, it looks like that we have a straight line that's going up from left to right. If we are having the positive slope, or as you go from left to right, you are increasing the function, then we say that the correlation is positive, or the coefficient of correlation should be positive, or equal some positive value. Now in this case, we do have a straight line pattern, but then we are going down the hill or decreasing from left to right, and if we have a decreasing slope, then we say that we have a negative correlation, or the coefficient should be a negative value. In this case, if I plot all the point here, and it looks like that we don't have a straight line going up or going down, there's no pattern in here, meaning that we don't have any correlation or no correlation. If we don't have any correlation, the coefficient should be 0. In this case, we do have something. It looks like a parabola, right? A parabola, or the function of a square, or the power of 2. And in this case, we do have the coefficient, but we don't have the linear relationship. We just have something else, or non-linear correlation. There are some requirements for linear correlation. The sample data, XY data, it must be a simple random sample, and make sure that it follow a straight line pattern, and there should not be any outliers, meaning that all the data point must go together. You cannot just have one point or one dot in here and the rest on the right side, right? There should not be any outlier, because if you have the outlier, it will affect the coefficient a lot. Now, we are using a lot of notations for the chapter, and here are the list of the notations, and usually represent for the number of the pairs of sample data. you can have 10 pairs, 20 pairs, right? Now this one is the summation notation, meaning that you're gonna sum all the thing inside here. In this case, the summation of x, meaning that you sum all the x value. This one meaning that you sum all the square of the x value, meaning that you square the x first before you add them. And the difference between here and here, this one is when after summing all the x together, you're gonna square the whole thing, right? That's different from this one. This one is you square the individual x and then you sum them or add them. Here we sum them all together and then the final value we square that. This one is that you take x and y, multiply together, and then you sum them all together. And R is a linear correlation coefficient for the sample data. Rho is a linear correlation coefficient for population of pair data. Okay, so the linear correlation coefficient R is measures the strength of a linear relationship between the pair values in a sample. And this is the two formula, and this is the expand formula for R. So you take n, or the number of the pair, multiply by the sum of all the x and y being multiplied together, and subtract the sum x times sum y, and take the square root of this whole huge formula. And usually we can use the TI-83 or 84 graphing calculator to find the coefficient in this chapter. We can do this by hand, but it's really hard. Take a lot of time for just by hand. We can just use the TI-83, 84, apply some technology, and it should give you the accurate value. Now, interpreting the value of R, we will use the table A6 from the textbook. If the absolute value after you compute the value of R exceeds or bigger than the value in the table A6, then you can make the conclusion that there is a linear correlation. Otherwise, there is not sufficient evidence to support the conclusion of a linear correlation. We can use software start this to compute the p-value, and if the p-value is less than or equal to the significant level, then you can conclude that there is a linear correlation. Otherwise, it's not. But I prefer we apply the table A6 for this chapter, because you have been dealing a lot with the p-value. So now let's try another way to visualize this. And there's some caution. The methods of this section apply to a linear correlation. Okay, if you conclude that there does not appear to be a linear correlation, and this is possible that there might be some other type that is not linear, but we are not considering that now. We are only considering for linear correlation at the meantime. There are some properties for linear correlation coefficient R. It must be between -1 and 1, and if all the value of either variable are converted to a different scale, the value of R should not change. And the value of R is not affected by the choice of x and y, meaning that you can switch x and y, and R should not be changed. R measures the strength of a linear relationship, and R is very sensitive to the outliers, which means that you don't want any of the outlier from your data. It will affect the value of R a lot. Now, the first example, we are given a pair zoo for the high data from 5 males, 1, 2, 3, 4, 5. So zoo with a high. Now we can use a TI calculator to find the value of the coefficient R, or we can use any technology, but we should be using the TI-83. And first, make sure you can check the requirement, but usually it should be a linear one if they are asking you. Now the data are simple random sample. The plotted points appear to be linear, so you can see it's kind of going up from left to right. So this can be a straight line pattern. It's not like it's everywhere. It's going up here. So yes, we have the straight line pattern, and there's no outlier. The outlier here, meaning that we have some point here, and that's just one point all the way over here, and this point should be the outlier. But in this case, we don't have the outlier because they are close together. Now, from TI-83, we can find the coefficient, the correlation coefficient R to be 0.5912, and R here is calculated by the formula, the Hughes formula here, right? We have to do all the sum of x, y, multiply them together, and plug in all of them. So it's really hard to do that by hand. But we have TI-83. Why don't we use that? Let me show you how to use that. So let me open my TI-83. Go back here. Oh, no. Okay. So from your TI-83, you're gonna turn on that first. So let me clear that. Quit. Okay. So first you must enter the data, right? So you go to the list here, click on start, and edit right here, click enter. So your L1 is your X, L2 is your Y. So I enter 29.7, and then I go to the next one, 29.7 for X, and 31.4 is the next one, 31.4, and 31.8, and then 27.6. So that is my X. Now I go to my Y, I enter 175.3, 177.8, 185.4 right here, 175.3, and 172.7. So after I have my X and Y listed here, I go back to just quit. Now go second, go to go back to start. Okay, and you want to go to calculation here, so click here, and you are working on the linear regression, which is number 4 here. This LIN is standing for linear. So we are dealing with linear coefficient correlation or the linear regression in this chapter. So go to number 4, and no, I think I click on the wrong one. Let's clear everything. So go to start again, go to calculation, and go to linear. How come this is not? Okay, I think I know that's what's wrong here. It's slightly different from TI-84. So what you have to do here is, once you have the list of x and y, now get out here and go back to stats, go to calculator, no, go to test. If you are using TI-84, then you can press on number 4 and it will give you the coefficient. Now if we are using the 83, then we go to test here, and then you are trying to find the linear regression test here. So linear regression test, so click enter and make sure that x is your L1, y is your L2. This is the value that we entered before. Now everything here is, you should keep them as a default value. So frequency is 1. These are the default value. So keep them the same thing and go to calculate, click enter. Now it should give you the coefficient R. So scroll down. R is 0.5912, right? So 0.5912. Let's compare that to here. Then yes, 0.5912. So this is how you apply the TI-83 or 83 plus to find the correlation coefficient R. Okay, so technology is really highly recommended for this chapter. Now, is there a linear correlation from the example we just did here? We found from the last example that R is 0.591, right? Now we need to proceed and interpret the meaning of that. Now our goal is to decide whether this is a linear correlation or this is not. Okay, so we can base on our p-value or a critical value from table A6. I'm not using the p-value in this chapter, so you can ignore that. We can just apply the table A6. Now let's go back to table A6. Okay, let me go back here. Okay, my table A6 here, this is from your textbook. We have 5 pair of data, right? 5 pair for the zoo. 5 pair of data, and if I take 0.05 level of significance, then I have 0.878. That's why here my R is 0.878 for 5 pair of data of 0.05 level of significance. Now the value of R is from -1 to 1, -1 to 1. Now if the table A6 give us 0.878, so we go from 0.878 up to 1, it's the region for the correlation, and also from -0.878 all the way to -1 is also the region of correlation. However, our value is 0.591 from TI-83. It is here, and it is not inside the correlation area or the region, either here or here. We are in the no correlation region. Therefore, we can make the conclusion that there's not enough sufficient evidence to support that our sample data has a linear correlation. So there should not be a linear correlation for our previous example. We can also use the R-square value, and R-square is the proportion of the variation in the Y that is explained by the linear relationship between X and Y. In the last example, we also got R-square equals 0.349, and I believe this one is also can be found from here, right? R-square, which is this guy. So this one meaning that we have 34.9% of the variation in the height can be explained by the linear relationship between the length of shoe prints and height, meaning that there's only 34.9%, which is below 50%. Therefore, it's another way to say that they don't have anything in the linear correlation. And there are some common errors involving correlation that you must pay attention. Causation. It is wrong to conclude that the correlation implies causality. So if you see that one thing X and Y, some value of X and some value of Y, they may be going together, but it is not necessary for one value of X that is the cause or the reason of the value of Y. They happen together, but they are not the reason or the real root of causing the problem. Okay, this is what is meant here. And the RX suppress individual variation, and it may inflate the correlation coefficient. Even if we don't get any of the correlation, but there may be some other type of correlation that is not linear, and we're not talking about that in this section. So correlation does not imply causality. Now part 2 is formal hypothesis test. Okay, so go back to the hypothesis testing. We wish to determine whether there is a significant linear correlation between the two variables X and Y. Notation. N is the number of pairs of sample data. R is a linear correlation coefficient for a sample of pair data, and rho is a linear correlation coefficient for a population of pair data. The requirement is similar to our last chapter. It must be coming from the simple random sample. It has to be a straight line pattern, and there shouldn't be any outlier. The null hypothesis, meaning that rho is equal to 0, or there is no linear correlation. Now the alternative hypothesis is rho is non-zero, or there is a linear correlation. We will use the test statistic R and compare that to the critical value, or refer to table A6. We can also use a p-value methods from previous chapters, but I'm not focusing on a p-value for this chapter. I want to focus on table A6 and the critical value. Now, if the absolute value of the R is bigger than the critical value from table A6, then we reject the null hypothesis. If we reject the null hypothesis, meaning that we say that this statement here is not true, or we conclude that there is a linear correlation, right? Or we support the claim of a linear correlation. If it's less than or equal to the critical value, then we do not reject the null hypothesis, or we say that there's no linear correlation. So it's bigger than the value from A6, there's a correlation or linear correlation. Now, in the last example, we found R from the TI-83 right here. Let me open that again. 0.591, right? We found R, and if we use table A6 for 5 pair with a level of significance 0.05, then 0.878, and of course this one is less than 878, right? If it's less than, meaning that we do not reject the null hypothesis, or we say that there's no linear correlation, or there is not enough evidence to support for the claim of a linear correlation, meaning that this one is we are accepting the null hypothesis, or there shouldn't be any of the linear correlation. So no linear correlation for this example, because this one 0.591 is less than 0.878 from table A6. Less than, no linear correlation. And then we can use a p-value, but I'm not using this for this chapter. So we're only focusing on finding the R and compare that to the value from table A6 and make the conclusion. And that should be the goal for this section.